Geomatics Engineering from Toosi University in Tehran, from Department of Interferometry and Remote Sensing. I did my Ph.D. in University of Calgary in Canada. I did use the radar Sat2 data for forest monitoring in Canada. And also I had a postdoc in the Netherlands, University of Twente ITC, in which I used the interferometric star data for the deformation analysis of the geothermal plants in Indonesia. That was my project in ITC. So the topic of today's talk is about the radar remote sensing. Sure. The radar remote sensing, mainly the basics and applications, and also some comments on the land deformation using the radar data. So I divided my talk into two parts. First part is I give you some basics and principles of radar remote sensing. And the next part would be some like the main concepts of interferometry, for which we use interferometry for using the DEM, for generating the DEM, and also the displacement map. That's my main plan for today. And honestly, this is my first presentation that I don't know really where to start, because people are from different backgrounds. And as far as I know, you guys didn't have passed any courses in radar remote sensing or radar analysis, macro remote sensing. So I need to give you some basic ideas at the beginning, and then I shift to the applications. So basically, in terms of the, let's say, electromagnetic wave spectrum, there are three types of remote sensing. The first one is the optical remote sensing. The optical remote sensing covers the visible and near infrared part of the spectrum. And also the second part, which is the thermal part, which is called thermal remote sensing. It uses the thermal infrared. And the last part is the microwave remote sensing. In microwave remote sensing, we have both passive microwave and active microwave remote sensing. The focus of my talk here is on the active microwave remote sensing, in which we ourselves send the signals toward the ground. For the first one, which is the optical, we use the term reflectance, which is coming from the ground. For the second part, we use the radiation or emission, which is coming from the ground. And for the case of the microwave, or from now on I say radar remote sensing, the term is backscatter. I mean, the amount of energy coming from the ground is called the backscatter. So, actually, the part of the spectrum that the microwave remote sensing is using is from a few centimeters to 1 meter. So, as you know, the wavelength is much longer than the optical one, in which just it is a few microns. So, this will bring us a lot of advantages comparing to the optical remote sensing. I listed some of the advantages of the radar remote sensing. It is all-weather imaging capability. Because of its longer wavelengths, it can penetrate through the atmosphere. It can penetrate easily through the clouds. So cloud is not like a limitation in the radar remote sensing. It has the possibility of the day and night acquisition because it is not dependent to the sun. And it generates its own source of energy. So it can take images during the day and night. There is no effect of atmosphere, I told you, and also it is very sensitive to dielectric properties of the objects. And I will tell you what exactly the dielectric constant is. And also it is very sensitive to the surface roughness, and this is also because of its long wavelengths. And usually the roughness, which is not visible to the optical remote sensing, it is completely visible in the radar remote sensing. And also it is very sensitive to the man-made objects, and also the target structure is also very important here. It can have a very accurate measurement of distance, and the technique is interferometry. I will tell you about that at the second part of my presentation. And also it has a partial penetration through the soil, through the target. Especially when the soil is dry, it can like penetrate a few meters through the ground. So basically we can have information like below the ground, which is not the case in terms of the optical remote sensing. And also there are some disadvantages. The interactions are usually very complex. It's not as easy as the, let's say, the optical remote sensing. And the type of the images that we are taking are, we are calling the coherent summation of the signal from the ground. I will explain it more. We have a speckle effect. The images look a bit noisy because of the speckle phenomenon. The topographic effects sometimes can cause some problems for us, and also the resolution is not as good as the optical remote sensing. Although the recent generation of the SAR remote sensing have better resolutions, but still it is not comparable to optical remote sensing. So here you can see two images, one radar. The images are from Ireland, and they have taken in the same day, the same time approximately. One of them is radar and the other is optical. Which is radar and which one is optical? Quite clear. So the left one is the radar image, quite clear, but the right one is the the optical image, and the cloak is a very big problem with that image. This is another example. The left one is the radar image, the right one is the optical image, the visible optical, and the cloak is the main limitation here. Radar is an acronym for radio detection and ranging. So based on that, actually what a radar do is three basic things. First, the antennas transmits the signals toward the ground. This is the first thing. So the signals, which we call it the pulses, are transmitted toward the ground. And after an interaction with the objects in the ground, an amount of backscatter, a portion of the reflected energy is coming back to the antenna, which we call it the backscatter. So this is the three basic things that radar do for us. And what exactly is receiving at the antenna is a distance from the radar to the object, which can make the location of the objects for us. And also, it is possible to measure the strength of the signal from the ground. So here you can see how a line of image can be formed in a radar image. These are two. Let's say this is a tree, this is a house, and the signals are transmitted toward the ground. These are the pulses which are transmitted to the ground. And based on the type of the objects, we will have different amount of backscatter. For example, in this case, in case of the house, the amount of backscatter was larger compared to the tree. I will tell you why this is happening in case of a house, or any kind of man-made objects usually have a larger amount of contribution or larger amount of backscatter in the image. So that's why we will have a peak here, a very bright part here, a smaller part, and the location is formed based on the time that is received, because the signals are transmitted and then received, so the difference in time can be measured, and based on that difference we can calculate very exactly this object should be formed in an image. So the final image for this would be this line of image. See, this is the energy coming from the house, which is very bright in the image. No energy from this part, so completely dark. And this is like the energy coming from the tree, so a bit gray here. And this mechanism, this procedure is performed line by line, and then we can have a full scene of an area. This is mainly the geometry of the radar imaging. We have a few terms that I want to introduce in the beginning. And please, if you have any questions, please interrupt me, because it is a long talk, so I just want to explain the things clearly. So if you have any kind of concern or comments, please interrupt me. This is the flight direction. We sometimes call this one azimuth direction. This is the range direction. The range direction is the direction that the signals are transmitted toward the ground. This is a nadir point, and also this is called the swath width, from which we can form the image. This is the near range, this is the far range, and so there are two directions here. Azimuth direction, which is the direction of the flight, and also perpendicular to that, we call it the range direction. The range direction, as I told, this is a slant range direction. The slant range direction, when it is projected over the ground, we call it the ground range direction. And in this image you can see these terms more clearly. This is this is a look angle. Because in radar, the aircraft does not like measure the bottom. It is like it is a side-looking mechanism. So the signals are transmitted toward the ground, and from a near range to a far range, a swath speed is collected. And this is also called the look angle, and this is the incidence angle. Incidence angle, the look angle. If we neglect the Earth's curvature, we can say that look angle and incidence angle are equal to each other. And also this is called the depression angle. So these are the main terms that we're going to use. And also we have, this is the incidence angle I told you, and this is a local incidence angle. These two terms are different. This is incidence angle, this is the local incidence angle. So, can anyone tell what is the difference between a local incidence angle or an incidence angle? In which cases these two terms are equal? Yeah, if it is flat, so these two terms are completely equal to each other. But basically, incidence angle is a sensor parameter. But local incidence angle is a target parameter. You know what I'm saying? So if you have different slopes, the local incidence angle depends on the slope of the area. Whereas the incidence angle is like a sensor parameter, an antenna parameter. For example, one antenna transmits with a 30-degree incidence angle, another one transmits with a 40-degree incidence angle. So it depends on the sensor, but the local incidence angle, it depends on the slope, the local slope. The local slope will have effect on the local incidence angle. So with this introduction, and I want to give you some information about the backscatter. What the backscatter in radar means. As I told you, the backscatter is the amount of energy or the portion of energy that is coming back to the antenna, and the antenna receives it. So in this part, I want to explain what parameters can change this amount of backscatter, what parameters can increase this backscatter, what parameters can decrease this amount of backscatter. So if we know the influencing parameters in the backscatter, then we can easier interpret the radar image. If one part of the radar is like brighter than the other part, then we can like interpret, analyze why this is going to happen. So targets with high backscattering usually are brighter, and targets with low backscattering are darker in the radar image. The influencing factors in terms for the backscatter depends on two things. First are the characteristics of the target, and the second are the characteristics of the sensors. So I start from the characteristics of the target. We divide these parameters into four. First, the geometric shape. The second is the surface roughness, dielectric constant, and local incidence angle. I told you the local incidence angle is a target parameter. So I explain them one by one. First, I start with the geometric shape. Actually, the geometry of the target has a great influence on the amount of backscatter. The targets with different geometry can have different amount of backscatter toward the antenna. For example, if the scene is agriculture or a forest, or forest with different heights, the amount of backscatter generally changes. There are a special type of targets in this category which we call them coherent targets. If we have coherent targets in the ground, then we can say that the amount of backscatter is very large for the coherent targets. A significant amount of energy is coming back to the antenna. So what are the coherent targets? The coherent targets, which we call them also the corner reflectors, here are divided into three parts. Some of them could be a top hat corner reflectors. A top hat corner reflector is basically a cylinder-like object which is on the ground. And if you see here, when the energy comes back to the ground, then it's bounced to this, like this object, and the total amount of energy is coming back to the sensor. We call this type of scattering a double bounce scattering, because there are two bounces happening. One bounce of the signal to the ground and another bounce to this object, and then most of energy is coming back to the sensor. So these type of targets are usually appeared very bright in the radar image. We also have a dihedral, which is basically two plates which are perpendicular to each other. Here again we have a double bounce. I mean, one bounce to the ground, another bounce to the plate, and the total energy coming back to the sensor is too high. So these type of energy, which we call it coherent points, coherent targets, are very bright in the radar image. And also it could be like a trihedral, like 3 plates. So again, the same scenario. Most of the energy after bouncing to these plates and also to the ground are coming back to the, let's say, radar antenna. And again, a very bright object will appear in the image. Generally, we have 2 types of target corner reflectors. The corner reflectors could be the man-made corner reflectors or the natural corner reflectors. The man-made corner reflectors are such as the calibration targets, buildings, bridges, all the urban area, for example, are consist of the buildings, towers, posts standing in water. These are like the man-made objects, which we call the corner reflectors, and also the natural one. For example, the rock, which are facing like by joints or faults to the antenna, trees standing in water. I emphasize in water because water has a very large impact on the amount of, let's say, backscatter. So I will explain why water has a large amount of, let's say, impact. And also the land-water interfaces could be the natural corner reflectors. If you look at this image, this is a radar image from the northeast of Iran. Here we have a city of Ardabil. It's an urban area. So if you and the surrounding parts are mainly the agricultural areas. If you compare this part to this part, it's very bright, and the main reason are the existing of the corner reflectors, like the buildings, like the towers, whatever, in the city, and but the other parts are very, like, let's say, dark. Here there is another city, which is like this is the Caspian Sea. Here is Astara, another city in the north of Iran. And again, you can see it's very bright. It consists of a lot of corner reflectors. That's why it appears very bright in the radar image. And what is this image? Yeah, this is like a port. And there are a lot of ships here. And that's why one of the main applications of radar images are for ship detection. Because the ships are very quite clear in the radar image. You can see it's very busy port actually. And so they are corner reflectors, so they can backscatter a large amount of energy toward the ground. Yeah, that's it. This was the first parameter. The second parameter which have impact on the amount of backscatter is surface roughness. The roughness of a surface is a very important parameter for let's say, the amount of backscatter that is coming to the antenna. In this case, we can have like smooth surfaces or rough surfaces. The main difference when the surface is smooth, then let's say very small portion of the energy is coming back to the antenna. Whereas where the let's say the surface is rough, then we will have a larger contribution, larger portion of the incident energy toward the antenna, and that's why a rough surface is usually appear brighter than the smooth surfaces in the radar image. Here it is, let's say, for smooth surface, a medium surface, and a rough surface. You can see for 1, 2, 3, the amount of backscatter is different. The largest amount of backscatter is for the case 3, which is a rough surface. And from the amount of energy, there are some backscatter one in this case. Whereas in the 2 other one, maybe there are very small amount of backscatter energy, and that's why they could be appeared very dark. But the term roughness does not have an absolute value in radar imaging. You cannot say this surface is rough, this surface is not rough. Usually the term roughness in radar remote sensing depends on the, let's say, the wavelengths. The wavelengths of the energy that are transmitting toward the ground. So for one wavelength, a surface could be appeared as rough, but for the other one, it could be smooth. So it depends on the, let's say, the wavelengths. So we can categorize a surface to be rough or not. For example, here, this is X-band. X-band, the wavelength is 3 centimeters, and also we have L-band. The wavelength is 25 centimeters. Right? Let's see which of the following surfaces are rough for X-band and which of them are rough for L-band. The first case, for the both X-band and L-band are considered as a smooth surface. So both X-band and L-band are considered these two surfaces as smooth. What for the second one? The second one for the X-band is rough because it's 3 centimeters. So this kind of relief is considered as rough for the X-band, whereas the same roughness for the L-band is not rough. It is smooth. You know, so when the energy is transmitting in the L-band, most of the energy are not coming back to the antenna. The same surface, but for L-band, it is smooth, but for X-band, it is rough. So, and also these two cases, for example, the same surface, for the case of X-band, it is very rough, but for the case of L-band, it is rough. You know what I'm saying? So when we call a surface to be rough or smooth, it depends really on the wavelengths that the antenna is working. If you look at this one, we can discriminate different types of surfaces based on their roughness. For example, here we have mud, here it is mud, and here is limestone. Limestone is, can be seen as brighter than the mud, and the main reason is their roughness, because they have different roughness. The roughness for limestone is, as you can see here, is larger compared to the mud. So a larger portion of the energy is coming back to the antenna. So, but this case is usually not the case in the optical remote sensing. The optical remote sensing is not sensitive to the roughness, because you know the optical remote sensing, the wavelengths are a few microns. A few microns are not enough to see the roughness. Whereas this 3 centimeters, 5 centimeters, 20 centimeters wavelengths, 1 meter wavelengths are quite enough to be sensitive to the roughness of an area. And here, as you can see, another example, this is an ERS image. ERS is a European satellite which was launched in 1995. It's a radar antenna, and it was working in C-band. C-band is about 5.8 centimeter, the wavelength. It's from France, and some part of this image, as you see, are like very dark. Can anyone make a guess why these parts in radar image are very dark? What parameter or what kind of objects could be there? What is that? No. What is that? Depth. No, not depth. Not depth. It is oil. Oil spill. So why oil spill is very dark in a radar image?
It smooths the surface.
Yeah, exactly. So the thickness of the water changes when there is oil on it. So when the thickness becomes like more or thicker than the other part, it is like smoother. When it is smoother, it means that it can backscatter less energy to the antenna, and that's why one of the main applications in radar imaging is oil spill detection. And I'm saying this is one of the main applications in radar imaging. Yeah, you can see here. This is the oil sheet, which is smooth compared to the neighboring area. And again here, I use the same image. You can see the water is always black. And it depends on the wavelengths as well. Maybe in some wavelengths it is not. But in this case, it is black because it is smooth. So maybe, but if this image is from C-band, if we use the X-band in this case, maybe we would have some amount of backscatter, but in the case of C-band, it's completely black.
the minimum amount of the oil that can be detected by this system, how much it must be?
Basically, it depends on the resolution of the system. You know what I'm saying? For example, when most of the C-band antennas have the resolution in the unit of, let's say, 5 meter by 5 meter by 10 meter, 5 meter by 11 meter, or when we decrease the resolution to X-band, the resolution would be like 3 meters to 5 meters, 2 meters to 4 meters, around that.
But
so if it exists...
The oil is scattering in different places. It's
yeah.
not possible to keep it in somewhere and then use this system in order to detect this oil loading.
Yeah, I know. But it still can cover some areas in the range of the antenna that can be sensitive to. You know what I'm saying? Well, you're right, it can be scattered in different areas, but it is still sensitive. You know, I mean, that part is still on the, like the resolution cell of the antenna. That's why it can be seen from the antenna. Another term that we use here is volume scattering. Volume scattering is a multiple scattering of the signal in the target. Because, you know, in case of the radar, the signals can penetrate through, for example, canopy. When we have canopy, the signal penetrates through the canopy. When it penetrates, we will have a multiple bounces, a multiple scattering of the signal, and then we will have a contribution coming back to the antenna. This term is called a volume scattering, and that's basically dependent on the amount of penetration toward the objects. And it usually happens for the vegetation area, for the forest area, in which we have such a kind of objects in which the signal can penetrate. Again, for the like the scattered contribution of the forest area are different types. Maybe one signal is just coming back from the top canopy. Another signal could penetrate and just scatter inside the canopy and then come back to the antenna. Another one could like bounce to the ground and maybe like have a double bounce to the tree and then come back to the antenna. So the amount of penetration depends on the wavelengths. If the wavelength is higher, the amount of penetration through the canopy would be higher. So I will explain about this parameter when I go to the wavelengths.
As you call it, first pulse and second pulse.
Yeah, but that's the term we use in LiDAR actually, the first and second. But in radar we don't use usually that term.
Excuse me.
Yeah.
2 slides before you showed the subsoil surface.
Yeah.
So can you explain that penetration level, how much it can...
yeah, that's a good question. Actually, even in the soil we could have the penetration, but the amount of penetration depends on 2 things. First, on the wavelength of the radar. If the wavelength is larger, the amount of penetration will be higher. And the second is the dryness of the soil. If the soil is completely dry, I will show you later about this. If the soil is completely dry, then we will have a large amount of penetration through the soil. But if it is wet, then the amount of penetration will be very small. Yeah, I will explain about this in the dielectric constant part. Yeah, third part is dielectric constant. The dielectric constant is usually talking about the material's electrical properties. How much material can absorb energy, how much the material can reflect the energy. These kind of properties can be explained by the dielectric constant of that material. So we want to see what kind of materials have high dielectric constant and what kind of material have a low dielectric constant. When we are talking about high dielectric constant, it means that no absorption. That material does not absorb the energy at all. So with high dielectric constant, we have water, we have salt, metals, living vegetation. Then we say living vegetation, it means that it consists a lot of water. That's why the amount of the dielectric constant increases. The low dielectric constant is rocks, lake ice, dry soils, dry sands, dead vegetation. These are the low dielectric constant. So the low dielectric constant materials absorbs more energy compared to the high dielectric constant. This is an image of a vegetation area, agricultural area after rain. When raining happens in an area, you can see the image looks very bright. It looks very bright. What is the reason?
The amount of black scattering?
Yeah, increases, yeah. Why?
Because it cannot penetrate so much. So
Why?
It's because of the properties of the water.
Because of the water has a large amount of dielectric constant, so it does not absorb, it means that it backscatters all the energy. So, if this is the case, so why these areas looks completely black? These are water areas. How can you interpret this part? I say that these vegetation areas consist a lot of water, that's why they looks bright. So, why this lake, the sea, as I showed you before, they are completely black? Why?
No energy is coming back from there.
Actually, this part does not absorb any energy, but the main point is that because of their roughness, they do not reflect it toward the antenna. The energy is coming back to the another direction. It does not absorb, but does not reflect it back to the antenna. That's the main point, that the sea areas, the lakes looks completely black. This is an agricultural area. So can anyone say what are these circles?
It's for vegetation, and when you want to make it with water, watering them, and it's the whole circular, you can see it.
Yeah.
Agriculture in the desert.
What is that?
Agriculture in the desert, like sprinkling water.
Yeah, we call it the central pivot irrigation. Central pivot irrigation. It's a type of irrigation. So those parts which are brighter, it means they have recently been irrigated. Those parts are dark, it means that maybe a few days ago, irrigation was for a few days ago. And it's circular because the system is central for irrigation.
Do you have any specific interpretation key as like optical remote sensing as well as radar remote sensing?
Can you say the question again?
Do you have any interpretation key, standard interpretation key, visual interpretation key as like optical remote sensing?
In optical remote sensing, we never sense these differences. I mean, we never see these kind of differences between the amount of irrigation, because the optical remote sensing is not sensitive to dielectric constant. You know what I'm saying? But this sensitivity is very high in radar remote sensing. They're quite discriminated from each other. So that's why another application of the radar remote sensing is soil moisture extraction. Soil moisture is very popular in the community of radar imaging because soil moisture, it has very high dielectric constant and it has moisture, so it can be like better sensed from a radar image. And if you remember, I told you when I was talking about the corner reflectors, I was talking as an example, for example, a post standing on water. Posts standing on water or trees standing on water have a very we call them coherent points. What was the reason? You can see the first bounce to the tree, another bounce to the ground and coming back, or the other side. First bounce to the ground, to the tree and coming back. When it has water, the amount of backscatter is larger. I mean, when the first bounce, this is a flooded area. When the first bounce is on the flood area, the flood does not absorb any energy, so it bounces all the energy to the tree, and then a larger amount of energy comes back to the antenna. For flood detection, also the radar remote sensing is very good. Especially in the forest area, when there is flood, the signals can penetrate toward the ground, so the amount of flood mapping could be a very good application in radar imaging because of this reason.
Excuse me.
Yeah.
Can I interrupt? Previous slide. From what you say, if there is a rice field which is completely flooded, it will look dark.
Yeah, it is.
But if it is half filled with water, it will look bright.
Bright, yeah. That's why the rice mapping is also a very interesting application, because we usually acquire images in different stages of rice, because rice mapping have different stages. The first one, it is completely floated in water, and in that stage it is completely black. In the second stage, maybe it looks brighter. So if you look at multi-temporal behavior of the rice, then it would be very interesting application in radar imaging.
So here point B could be completely flooded also.
This part
Point B. Point B.
Point B.
Could be completely
Yeah, could
flooded.
be. Could be. It depends. Maybe either it is completely flooded, or maybe there is not any kind of like water in it. It is completely smooth.
Barren.
Yeah, completely smooth. Bare soil.
Bare soil.
Bare soil. If it is bare soil, then it is very smooth, so no amount of backscatter to the radar. So it depends. And the last parameter here is the local incidence angle. I told you the local incidence angle is a parameter of the target. So depending on the slope, we can have different amount of local incidence angle. But the thing that I want to mention here is that the lower the amount of local incidence angle, the higher is the amount of backscatter. The lower the amount of local incidence angle, the higher amount of the backscatter. Because when the incidence angle is lower, it means that the slope is completely toward the antenna. So it means that most of the energy can come back to the antenna. So the local incidence angle could be also another parameter which can affect the amount of backscatter toward antenna. And in case of the sensor parameters, there are four categories of parameters. One is wavelengths, another is incidence angle, polarization, and look direction. I try to explain them faster because the main part of my presentation is the second part, which is on the interferometry part, so these are just the basics. So in terms of the wavelengths, actually, there are different bands in radar remote sensing. It usually starts from X-band. X-band satellites like the TerraStar, TerraStar has the X-band satellite, the German satellite. And it works in this range, about 3 centimeters. And also after X-band, we have C-band. C-band is around 5 centimeters. The wavelength is about 5 centimeters. And the main example here could be the radar sat image. The radar sat, the Canadian radar sat image are C-band. And also another popular example is L-band. L-band, the wavelength is higher. It's about 20 centimeters or something. And the example here could be the ALOS images. ALOS is a Japanese satellite. And they had ALOS 1, which was built in 2010, and recently they launched a new ALOS 2 satellite. So the question is, what type of wavelengths should we use? What type of wavelengths should we use in our case? It depends on the application that you are using. If you want to go, for example, in forest application, we usually interested to have a higher penetration through the canopy in order to have information from the canopy, from the bottom, from the tree, from the trunk. So if if the penetration is very important for you in application, then you should go for L-band, higher wavelengths. If, for example, the penetration is not that much important, for example, in case of the urban areas, you can use the X-band images, or for vegetation area, agriculture application, the C-band works very good. So what kind of image to select it really depends on the application that you're going to follow. And here, as I told you, the penetration depth is very dependent to the wavelengths that you are using, and also the relative roughness. I talked about the roughness previous, and I told you that the roughness is not an absolute term. It depends on the, let's say, wavelengths that you are using. In one wavelength, one surface can be considered as rough, and in another surface, it can be completely smooth. Here you can compare the X-band, C-band, and L-band in a forest area, for example. In X-band, all the signals are coming back from the top canopy, no penetration. In case of C-band, we will have some amount of penetration, so we will have some information from the inside the canopy. Whereas in the L-band, the penetration is higher, so we can have even some backscatter from the ground. You know what I'm saying? So if, for example, flood mapping is an application in the forest area, you should go for the L-band. Here also for soil, snow, whatever, here in case of the snow you can see the amount of penetration is different wavelengths. And one thing about the snow is that the snow should be dry snow. For wet snow, we do not have any penetration. For dry snow, there are some penetration, especially in the longer wavelengths. Yeah, this is in also again in trees. L band, C band, X band, different amount of penetration, different amount of backscatter from different parts of the tree. X band, L band, P band. P band is larger. I mean the amount of wavelengths is larger than the X and L. And this is what really a radar see from the trees in different wavelengths. An X band image can see the tree like this. Whereas the L band image see the tree like this. I mean, in an L band, it is not sensitive to the leaves because it penetrates through the leaves. But again, the twigs, the main branches are still clear in the L band. In P band, only the trunk and the main branches can be visible. It does not see any kind of leaves or twigs. And if you use a larger wavelength, this is the tree. Just the main trunk is visible. So really, the wavelength has a very large amount of contribution to the amount of backscatter. And here you can see different, from the same area, different wavelengths. X band, C band, L band. And it is not like the optical remote sensing that one satellite takes images in different wavelengths. Each satellite has just one wavelength. You know what I'm saying? For example, in case of Landsat image, we have different bands and different wavelengths, but here is not the case. Each satellite can collect just one image, and usually a color composite could be very informative, and because this sort of energy, this sort of images are information are completing each other. So usually when you combine these images, a very good image of the area could be formed. We have also incidence angle effect. As I told you, the images can be taken from a low incidence angle up until a large incidence angle. And this is mainly about the airborne radar remote sensing. In airborne radar remote sensing, there is a large variation in the amount of incidence angle. It can collect the images from maybe 20 degrees up until 45 degrees in case of the aircraft. Airborne remote sensing. But when we are using the spaceborne remote sensing, the difference is not that big, like 2 degrees difference between the near range and far range. For example, the radar sat can collect between 28 to 29, or 30 to 32, whatever, just 2 degree difference in one image, not a large variation in the incidence angle. I just want to skip some parts to go to the main part of my speech. Yeah, this is also the polarization. Another effect is polarization. Polarization of in radar is a direction that the signal is transmitted to the ground. Because we are transmitting the signal, we can define the polarization. It can be horizontal polarization, or it can be vertical polarization. So the direction that the signal is transmitted to the ground is called polarization. So here you can see this is the horizontal polarization, this is called the vertical polarization. So when you are using different polarization, different kind of interaction on the objects are happening, and different amount of backscatter are coming back to the antenna. For example, if there is an object which is like a perpendicular object, like a tree on the ground, and then you send a vertical polarization, then the amount of backscatter will be higher. I mean, the direction of the polarization is very dependent on the objects on the ground, and some objects can transmit back a larger amount of backscatter in one polarization compared to another polarization. So we can have different types of radar here. One radar could send a vertically polarized energy and receive only the vertical, we call it VV. VV means sending in vertical direction and receiving vertical direction. It could send in horizontal direction and receive in horizontal direction, we call it HH. And it can send in horizontal direction and receive in vertical direction, we call it HV or VH, the other side. And based on this, we call them light polarized or cross polarized. When they are similar to each other, HH and VV are called light polarized, and these two are called cross polarized. And basically there are, let's say, 3 types of radar here. Single polarized radars. A single polarized radar can only collect one of the polarizations, HH or VV. For example, the radar satellite was a single channel satellite. It was working in VV. Dual polarized can collect 2 of them, HH and HV, or VV, VH, or HH and VV. So this is called the dual polarized. And when we are talking about the polarimetric satellite, it means that all the channels are collected. HH, VV, HV, and VH. And this is the most complete type of radar image that are available at the moment. I mean, the full polarimetric satellite, and the RadarSat-2 image was the full polarimetric satellite. The recent Sentinel-1 data are dual polarized. And as I told you, the type of scattering is different in different objects. You see here? It's comparing the horizontal polarization with vertical polarization with different objects. For example, in a canopy, this red one is the horizontal, and this blue one is the vertical one. So, what do you think? Which one backscatter larger amount of energy, the vertical polarization or the horizontal one here? Yeah, the vertical one actually. The vertical one, as you see here for the C, this is the received amount of energy. The received energy for the canopy is higher in the vertical direction compared to the, let's say, the horizontal one. What about for this trunk? Again, the vertical polarization will have a larger amount of contribution compared to the horizontal one. You see here, the blue one is larger. What about for this, if the tree is like this, the structure? Vertical, horizontal, like this one. The horizontal one has become larger compared to this one. But still, vertical has a larger contribution. And, oh, sorry, here. Yeah, it was here. The canopy. The horizontal one, yeah, you're right. The horizontal one has a larger amount of backscatter. But here for the trunk, again, the amount of the, let's say, vertical one is larger than the horizontal one, but it is higher compared to the previous one. So based on the type of objects, we can have different amount of contribution from different targets in different geometries, different structure. And that's why we say that the radar is very sensitive to geometry. This is not the case in the optical image detection. Yeah, again, the polarization, you have single bounce, multiple bounces. Yes, this one. And again, you can have different polarizations, HH, VV, HV, and a color composite. This is the color composite of the 3 images. In a color composite, when we have different polarization, the amount of, let's say, information would be higher because these information are complementary, they are not redundant. So,
are the polarizations used parallel at the same time?
Yeah, they are received at the same time, yeah. Mm-hmm. When we are having a polarimetric satellite, it receives all types of polarization, VV, HH, and HV. Mm-hmm. So all the polarizations are received at the same time. But this was not the case in terms of the wavelengths. Each satellite is working at one wavelength. And the look direction is also important. You know, in radar remote sensing, we have both ascending and descending. We have ascending image and descending image, whereas in the optical remote sensing, we just have ascending image. Why? Why in optical we do not have the ascending, the orbit?
It's passive. The optical one is passive.
It's passive, and because the descending can also collect images, but it is at the other side of the Earth, so it is dark. Oh. It is during the night. So during the night, we cannot collect images in the optical remote sensing when it is descending. When the orbit is descending, it is night. But here, in the radar remote sensing, both images can be collected, both ascending and descending, because it is not dependent to the sun. It's sending its own source of energy. So loop direction could be important, and with different loop direction, We will have different amount of backscatter. This is the ascending image, this is the descending image from the same area. Okay, so this was the first part of my presentation. If you have any question up to now. Yeah.
I have questions on the application side. You mentioned different bands are used for different applications. What about identifying the rocks? Which band is suited for identifying the rocks?
For what?
Rocks.
Rocks.
Yeah.
Yeah, you mean in geology?
Geology.
Geology. In geology, actually, the roughness is very important. I mean, the parameter that we discriminate different types of minerals, for example, in radar remote sensing is difference in the roughness. You know what I'm saying? So if we could select a wavelength which is sensitive to the specific roughness that that type of mineral has, then we can have good information. I mean, the only parameter that is affecting here is roughness. So usually in most of the geological applications I saw, they are either using in X band or C band. X band or C band are the most important one. Maybe if the penetration is very important, maybe because some applications of geology on the ground there are soil, so the rocks are beneath the ground. So if the penetration is important, you should go for the longer wavelengths. Yeah, P band or L band. So if you have an outcrop the geological rocks, then the X band or C band will be good. But if the penetration is important, you should go for the longer wavelengths. But see, the P band is not applicable in the space-borne. We don't have any P band space-borne yet. So P band is just airborne. But L band we have. So next part of my presentation are some advanced techniques here. And before I go to the advanced technique, I define what is phase here. Phase, I explained what phase is in the beginning. Actually, phase is a measure of how far the waves are traveled. This is called waves. Start from 0, 2 pi, 4 pi, 6 pi, whatever. And there is a relationship between the phase and distance. This is like the phi and the lambda, the d. The d is the distance that is taken. The wave has taken 2 pi d over lambda. Lambda is the wavelength, and d is the distance. And yeah, if the wave is traveled by one wavelength, lambda equal to d, then the phase will be 2 pi. Right? 2 pi is like a distance of a lambda from this part to this part. So the reason that I explained phase in the beginning is that in radar images, actually what exactly is received by the antenna is this term. It is not just the amplitude. All the applications that I taught so far were based on the amplitude only. But in the radar imaging, we do not have only the amplitude, we also have the phase. The phase, up to now we neglected the phase, but the phase is very important actually in many applications. So how this image is formed? Actually in radar image, this is a resolution cell. This is one resolution cell. In a resolution cell, there are lots of scatter. There are a lot of scatter in the resolution cell. And for each scatter, we have an amplitude A and a phase phi for each scatter. And here we have a coherent summation of these two. A coherent summation of these two will form the amplitude and phase for one pixel. We call this summation a coherent summation. Does anyone know what is the difference between a coherent summation and incoherent summation? When we are talking about incoherent summation, it means that there is not any phase. Just the amplitudes are collected, not the phase. But when the phase has a role like this, then this summation is called a coherent summation, not an incoherent summation. The optical systems are all of them are incoherent summation. You know what I'm saying? Just the amplitudes are collected. But here we have also phase, not just the amplitude. So that's why we call the radar image a coherent system, because phase is also collected here. So basically for each pixel we have an amplitude and a phase angle, And phase angle is a function of the distance from satellite to the ground. Is a function of the how much distance that is traveled to the ground. This is the image of a phase. You see? This is a phase image. The phase image is noise. It's completely noisy in a satellite image. You cannot see any kind of object in a phase image, in one phase image, actually, in a radar image. It's completely noisy. And so it does not have any use for us. So if you are using just one image, one channel, the phase information has no utility. It's not good in any application. It's completely noisy. Does not have any information. So, but it does not mean that the phase is not important. It does not mean that we should neglect the phase. When we are using two images, actually the phase difference would be a very good parameter. Then we are using two images. Then the phase difference between these two images could be, let's say, a very important parameter and has a lot of applications. So although the phase itself does not have any utility, but the phase difference would be a very important parameter in the applications that I'm going to talk about.
Excuse me, could you go back one slide? No, one. Yes. The phase is somehow related to the distance, isn't it?
Yeah.
Should there be some similar colors
in
neighboring pixels?
No, there are different colors. Because, in one resolution cell, there are a lot of scatterers.
Yes, okay.
You know what I'm saying? So a coherent summation of all these scatterers will form the phase.
Yes, and the wavelength is
so we have just one.
Small compared.
Exactly, yeah.
To a pixel.
To the pixel.
Okay.
That's what I'm saying, yes, yeah. So in two applications, we can say that the phase difference would be very important. The first application is the interferometry. In interferometry, we have two radars observing the scene, and for example, in a baseline, and then they are collecting images, and when we measure the phase difference, then the image is not noise. I will explain what this image looks like and what does image mean, but it is not noise. And also another application is polarimetry. In polarimetry also, we can have the phase difference between the polarization channels. These polarization channels are taking at the same time. So the phase difference between these polarization channels is very important and has a lot of information in it. Yeah, this is, for example, another example of polarimetry. And when we use polarimetry, all the scattering mechanisms could be discriminated. For this session, I just want to give you some information about star interferometry and how the phase information would be meaningful in a star interferometry system. In star interferometry, we have two antennas. Antenna 1, antenna 2, and there is a baseline between them. A baseline, for example, in the range of 90 meter, 100 meter, 300 meter, whatever. Between them, and they are collecting images from the same area. So we have two images. Image number 1, S1, A1, exponential minus j phi1. This is phase, this is amplitude for the first one, and this is the phase and amplitude for the second image, right? And if I write this phi1 over, converted in distance, would be 4 pi over lambda r1, 4 pi over lambda r2. And we have a term called interferogram. Interferogram here is the pixel by pixel phase difference of the image. You see, if you just multiply S1 to the conjugate of S2, S1 to S2, then you will have this A1, A2, this is the amplitude, and this is the phase difference. This is the phase difference of two images. And this is the definition of interferogram I told you in the previous slide. So here, the term phase is called interferometric phase. The phase difference is called the interferometric phase. And as I told you, the images should differ at least in one aspect. For example, in terms of temporal baseline, we have a spatial baseline. When we are talking about a spatial baseline, it means that the two images are collected at the same time. At the same time, there is like a big baseline, and there are like two antennas toward the sides of the baseline. Two images are collected. So one large spatial baseline. And when we are talking about temporal baseline, it means that the images are collected at different dates. The first image and the second image, the third image, for example, the orbit every 12 days, every 20 days, every 30 days, whatever. The images can be collected. In that case, the baseline is called the temporal baseline, not a spatial baseline. You can see here, this is a baseline, and there is one satellite. There is a big baseline over that, because this is called a single pass interferometry. A single pass interferometry. Just in a single pass, two images are collected in a baseline. And the most important example for this is SRTM. I don't know if you have heard or used the SRTM DEM. The SRTM DEM is like collected using a single pass interferometry. There is a big antenna here, like 90-meter antenna, and there are like two receivers at the two sides of the antenna. And using this technology, it can collect the DEM of the area, the digital elevation model of the area. But you can use also two satellites. One satellite take image, and the satellites go and take another orbit. The same satellite, but in two different orbits. This is called a repeat pass interferometry. So if the application is generating the digital elevation model, then which one should be used? If you want to generate a digital elevation model, basically the spatial baseline is very useful. You know what I'm saying? Because they are collecting at the same time.
Well, if the surface doesn't change,
both
could you use?
Yeah.
Yes.
If we do not have any kind of displacement
Okay.
during the collection, yeah, we can also use this scenario for the DEM generation as well. But this scenario is basically used for generating the displacement map. For example, one image is collected before earthquake, and the other image is collected after the earthquake. So the interferometric phase will give you the amount of deformation. Right? So this is the basic idea. Let's see. This is the first acquisition that we call it the master from the ground. The distance calculated. And before the second acquisition, we have a subsidence. There's a subsidence here. So when the second acquisition is coming, and again the phase is calculated, the phase is measured, the phase difference between these two images can give you like an estimation of the amount of subsidence. See? So there is a very small difference between these two. The first acquisition, the second acquisition, like a phase difference of like delta phi, and this will give you an estimation of how much is the amount of subsidence in that area. So this is the basic idea for the interferometric application. But you see, if the flat was Earth, if the Earth was flat and the satellite orbit were fixed completely, there was no effect of atmosphere, there was no effect of noise, and everything was quite normal. Yeah, that was the case. It was very simple, the calculation very simple, and the ground deformation can be easily calculated. But in practice, this is not the case. I mean, we have a lot of things, a lot of contribution in the phase difference. The phase difference is not only dependent to the displacement. You know what I'm saying? So here,
excuse me. Why did you say no atmosphere? Does atmosphere
change? I mean, for example, with the first collection and the second collection, the amount of turbulence, the amount of the cloudness of the weather cloudness or any atmospheric condition shouldn't change. If the atmospheric condition changes, it will have a small amount of contribution to the phase difference.
Oh, okay.
You know what I'm saying? Because it will delay the signal. If the atmospheric change, for example, in one case,
yes, I got it.
completely clear. The second in the slave image it is like cloudy, so it will delay the signal. This delay could have contribution in the signal, in the phase difference, which should be modeled. So here, actually, up to now we have seen this. We have the one image, the phase of the first image, which is completely noise. The phase of the second image, which we call the slave image. Again, it is completely noise, but the phase difference is not noise. In the phase image, which we call it interferogram, it is not noisy. It has information. There are fringes. You know, there are different fringes, and these fringes have information. Can tell us about the topography, can tell us about the displacement, deformation of the area. So both the master and slave are random, but the interferogram is not. Look at this equation. Actually, there are a lot of equations involved in the interferometry, but I just try to give the main ideas for you. So I try to skip the equation and just give you the main ideas. This is the core equation in interferometry. Get this one? This is the interferometric phase. Interferometric phase, which is the phase difference. And two of the parameters affect here are the topographic phase and the displacement phase. Topographic phase and the displacement, but there are also other parameters like the flat earth phase, atmospheric phase, and the noise phase. So these are all the influencing parameters in the interferometric phase: flat earth, topographic phase, displacement phase, atmospheric, and noise. So let's see what are these parameters are. At the first, if the purpose is to generate the displacement map, it means that you have to get rid of all the other parameters. So if the main purpose is to generate the displacement map, it means that you have to get rid of all the other parameters. The topography phase, the flat earth, atmosphere, and other. If your purpose is topography, I mean the digital elevation model, it means that you have to get rid of the other parameters. You have to assume that there is not any displacement between the first acquisition and the second acquisition, if the purpose is digital elevation model. So, anyway, the first part is to remove the flat earth, this term. So what is flat earth here? You see? The flat earth, which we call it the phase interferogram from a flat earth area, it means that even if the earth is completely flat, I mean you are working on a flat area, there are still phase differences between the neighboring pixels. Between this pixel and its neighboring pixels, there are phase differences. This is because of the geometry of INSAR. But this is systematic. This is systematic. Meaning this kind of phase differences is completely systematic and can be removed from the interferogram. So the first part, the first step is to remove the flat earth phase from the interferometric phase.
This is done by calculation.
Easy calculation, yeah. So if you know the parameters, we know all the parameters for calculating the flat earth phase. So it can be easily reduced from the phase, interferometric phase. And the result would be something like this. You see, this is the interferogram. And now you can see like a better patterns, like a good patterns of maybe topography or displacement or whatever. So here you have cycles, you know, from blue to blue to blue to another blue. There are cycles of colors, and each cycle corresponds to 2 pi. Each cycle of color here corresponds to 2 pi. 2 pi could be like topography or deformation or whatever. So after removing the flat earth, the interferometric first would be correspondent to topography plus deformation. So we just removed one of the parameters at the moment. The flat earth is removed, so now we have topography, deformation, and also maybe the atmosphere. So the second part is to remove the topography. To remove the topography phase from the original one. This was our equation. We already removed the flat earth. If the purpose is displacement, now we have to remove the topography. Because topography has a very big amount of contribution over the interferometric phase. Yeah, now I just want to show you how the topography can be removed. Before showing how the topography can be removed, I will explain a term which is called the height of ambiguity or altitude of ambiguity. With the altitude of ambiguity, if you know how the height of ambiguity is, then you can easily make a relation between the phase difference and also the topography. So the definition of the altitude of ambiguity is the altitude difference which is correspondent to a phase change of 2 pi. I mean, how much difference in topography is corresponding to 2 pi. This is the equation that we can obtain the height of ambiguity. And if you see there is wavelengths, we have the distance from antenna to the ground, we have the incidence angle, we have the baseline. For example, in case of an ERS, ERS is the European satellite, the wavelength is this, 5 centimeter, 23 degree incidence angle, R is 850 kilometer. If you just plug this information into this equation, you will come up with this one. Around 10,000 over B, with the unit of meter. 10,000 over B. It means that a 2 pi difference in the interferometric phase is corresponding to this amount of height difference or topography. For example, if the baseline is 100 meter, like the 100 meter here, then a 2 pi change of interferometric phase is corresponding to a height difference of 93 meters, right? Which is like this one is 100 meter, then this could be obtained. And if you, so this is very dependent on the baseline. See, the baseline is a very important parameter here. If you increase the baseline, what happens then? If the baseline is increasing, what is that? Yeah. So if the baseline is increasing, then the height of ambiguity will be decreasing. So if you have a 200 meter baseline, then a 2 pi change in an interferometric phase would be related to maybe a 40 meter height difference. So we can say that if for the higher baseline, if the baseline is higher, then the altitude measurement will be more accurate. So if the baseline is higher, the altitude measurement is more accurate. It means your ruler for measuring the altitude would be more accurate in this case. However, we cannot increase this baseline to whatever we want because there is a limitation for increasing the amount of baseline for that. You can see here, 2 interferogram here. This is for a 12 meter baseline and this is for a 60 meter baseline. 2 different baselines, 2 different interferograms. And in case of let's say, a larger baselines, the distances between fringes is smaller compared to the smaller baseline. And that's why I say that for a larger baselines, we will have a more accurate calculation of the topographic information. And also here is showing the amount of wavelengths. As you see in the equation, wavelengths are also influencing parameter, not only the baseline but also the wavelengths. So if we increase or decrease the wavelengths, we can also have a different amount for the height of ambiguity, as you see in this image. For the smaller wavelengths images, the distance between fringes is smaller compared to the L band. So we can say that for example, the terasar image could be a more accurate type of image for calculating the DEM because the wavelength is smaller compared to for example, the ALOS images. So it directly affects the, let's say, the fringes. So this is an interferogram. You see, this is the interferogram. And if we assume that there is not any effect of subsidence, for example, there is not enough subsidence, these interferograms are interpreted as the height differences. And this is the related DEM that is generated from this interferogram. The DEM that is generated from this interferogram. So if the fringes are closer to each other, then it means that the height there is a larger height difference in that area. There's a larger topography in this area compared to this area. You see? So this is how a digital elevation model can be calculated from an interferogram.
Can you discern if it goes up or down?
Yeah, it depends. Because usually they have a color bar. Color bar shows you when it is this, subsidence or coming up or coming down. It is from blue to red or from red to blue. The meaning is different. So it is like a phase difference. The phase difference is negatively increasing or positively increasing.
Okay.
How accurate this digital elevation?
Yeah, that's a good question.
Is it possible for flat plane?
What's
flat
that?
plane area?
To calculate the DEM, you mean from
area?
flat? Yeah, you can generate the DEM for any kind of area. So, but the accuracy is different. Actually, I put one slide in the application part and give you some information about the accuracy of the DEM. But at this one, I can say for the SRTM case, the vertical accuracy is in the order of 10 meter. 10 meter. 10 meter, right. But when you are using this technology for subsidence monitoring, the accuracy is in the amount of millimeter. That's totally different. For subsidence monitoring, it's very accurate. But for DEM generation, yeah. Actually, there are some involving parameters like the baseline, what baseline you are using, what wavelengths you are using. But generally, in the order of 5 to 10 meters, the accuracy of the DEM that is generated here. So let's come back to again to the original formula that we were discussing. So here the topographic phase can be removed because, as you remember, we had this equation. So if there was not any displacement, so all the phase difference would be related to topographic phase. We can easily calculate the DEM, right? What about if the purpose is calculating the displacement? Then what should we do? Then how should we remove this part? If the purpose is the main goal is to calculate the deformation, then how to remove this part? We should either have the digital elevation model before, right? We should have the digital elevation model of the area before, and then convert the digital elevation model to phase, and then let's say subtract that phase from the interferometric phase. This could be one scenario. So basically, if you have two paths, just two paths. The topography phase could be like subtracted using the existing DEM. So if let's say the purpose is to calculate the subsidence, you need to have the digital elevation model in advance from the area to remove the topographic effect. What about when we have three paths? I mean three images. One pass, two pass, and three pass. For example, two pass before the earthquake and one pass after the earthquake. Now we have another possibility. From the first two pass, we can calculate the DEM, the digital elevation model, and remove that topography from the first pass and the after earthquake pass. So if you have three pass, then you can derive the topographic phase from the interferometry itself. You don't need any DEM in advance. Yeah, and another part was atmospheric phase in the original equation. The effect of atmosphere should also be removed. If the two images were collected exactly in the same condition, atmospheric condition, the effect of atmosphere is very small. But if the effect of the atmospheric condition is changing during the acquisitions, then you need to remove this contribution as well. It has some mathematical equation behind that. I just skip this one, but you see here. This is an interferogram. This is an interferogram, and this is the flat area. After removing flat earth, we're expecting this part to be completely flat. No pattern, no fringes. But you see, there are some effects, and these effects are because of the atmosphere. Two acquisitions are in different atmospheric conditions. Yeah. And also we have unwrapping here. After all these corrections are made, we need to unwrap the phase. Unwrapping, as you see here, because you know what we exactly measure is in the phase difference is between 0 to 2 pi, or minus pi to pi. I mean, just the amount of phase that is received is this. For example, in surveying, when you are doing leveling between these 2 points, you are just the height difference are calculated. And then you need to make the final calculation to convert this into this one. This procedure is called the unwrapping. After unwrapping, these are the fringes. You can convert, this is after unwrapping, you know. It's completely like a smooth transition from a high topography to low topography. Could be visible in this unwrapped image. Or another example. This is a wrapped image, this is an unwrapped image. Okay, one example. There was a very big earthquake in the magnitude of 7.6 in Izmit in Turkey in 1999. And let's see how INSAR can estimate the amount of this disaster in terms of the deformation. So we had two acquisitions. First is the August 1999, before earthquake. And we also have another image after earthquake. This is September. So each radar image has an amplitude and a phase. The amplitude here in the interferometry, we don't need it, just skip that, we just need the phase. So we just calculate the phase difference between these two images, which we call it interferometric phase, and this is the interferogram. This is the interferogram after removing topography and flat earth. So the effect of topography is removed, the effect of flat earth is removed. So all these fringes are talking about the displacement that happened before and after acquisition, right? You can see this is like the same area. And let's interpret how we can analyze this interferogram. See here? Here we have no deformation. There is a blue color here. From one blue to another blue is one cycle. One cycle is related to half wavelength of deformation. This is a C band, so 5.6 centimeter, half of that would be 28 millimeter. So from one to another, it means that from this point to this point, there is a 28 millimeter of deformation. From this point to this point, there are two, like another fringe, double as much as this one, which will be 57 millimeter subsidence, or maybe uplift, I don't know. And again, 3 cycle, 85 millimeter, 10 cycles again, 283 millimeter, and 20 cycles would be like about 50 centimeter, right? 50 centimeters of deformation from this point to this point could be estimated in this interferogram. And this is the fault. This is the fault around which this earthquake was happening. And you can see around the fault, the amount of deformation is higher, and when we are getting further from the fault, the amount of deformation is decreasing. And usually we can, like this is the interferogram, and this is the elastic modeling. The geologists use this kind of elastic modeling for generating the, let's say, a kind of model how earthquake can affect the surrounding area. So there is a very good agreement between these, what is obtained from interferometry and what is the elastic modeling is saying. Yeah, and this is the earthquake that happened in 2017 in Iran, in around Mashhad. We call it the Sankt-Safid city. And I used this is what we use, a Sentinel-1 image. before and after earthquake. It was like 5 or 6, I think, magnitude earthquake. And this was the interferogram after removing the flat earth, after removing the topography. Sorry, this is after removing topography would be like this one. So this is the center of the earthquake, and this is how the earthquake affects the surrounding area, and you can estimate the amount of deformation in the accuracy around like less than a centimeter. I have actually a lot of applications here, so I don't know how much time do I have to explain basically some of the applications of interferometry here, so it depends on the audience.
5 minutes more.
5 minutes more, right. So, using the interferometry, we can actually two basic applications. One for depth generation, and another for like deformation map generation. There are two main topics for, let's say, applications. The first one is the SRTM. I told you about SRTM, a big antenna, like 90-meter antenna. And with the same technology I told you, the depth was calculated, and each pixel was about 30 meter to 30 meter for SRTM, and the let's say accuracy was about the horizontal accuracy, and the absolute vertical accuracy here is 16 meters in this case. Yeah, if you use, for example, X-band images are more accurate compared to the C-band images which the SRTM was generated. So if you use the TerraSAR-X, the German satellite, then the accuracy would be a vertical accuracy of 2 meters can be generated for depth generation. This is BAM. This is for earthquake displacement in the BAM area. This also we calculate this interferogram using these NVSAT data before and after earthquake, and you can see the main fault, and there are two centers in this equation. So a lot of information could be obtained from the interferogram that are generated here. This is before unwrapping, this is after unwrapping. This is again BAM, and you see, yeah, from the fault, in one side of the fault, because when there is an earthquake, in one side there is uplift, and in the other side there is subsidence. So about 30 centimeters uplift here, and let's say 17 centimeters of subsidence here, in the two different sides of the fault. And this was also this was, I can say, the first interferometric application in the community of INSAR, and is related to the landers in California in 1992. We had an earthquake, and in that time nobody could believe such interferogram, and this work was published in Nature, and the cover page of the Nature was showed the interferogram of this earthquake. It was a 7.3 earthquake in that time, and you see all the information about the, let's say, yeah, here. This is the interferogram, the fault, all the amount of deformation can be calculated fringe by fringe, and yeah, the average displacement along the fault was about 3 meters in this case. Yeah, and also there was a very good agreement with the elastic modeling of the earthquake. They completely match each other. But using this one, a very detailed pattern of deformation can be obtained. This is a very general one, but this is a very detailed one. Yeah, another example in South Napa, again in earthquake. You can generate the interferogram, you can unwrap it, and then calculate the amount of displacement. Here, for volcano monitoring, you can use the different interferometric star image. And if you look at this one, this is a volcano. So different interferograms can be seen in different times. And you see, if when the volcano starts the eruption, then the amount of, here is uplift. The amount of deformation is quite clear. And by this time difference, you can exactly monitor how the displacement is occurring in the volcano. It's like it needs a time series actually. This is for plate tectonics. Actually, here are some oil and gas fields. You can see these are oil and gas fields when you are subsidence in the oil and gas fields. You see? Also, here we have plate tectonic here. In one side there is uplift, in another side it is subsidence. We have different mechanisms happened here. We have landslide. For landslide monitoring, is also interferometry SAR is very useful. Yeah, the amount of landslide between two images could be quite clear in this image. You can see here, when it is negative, it is subsidence, it is positive, it is uplift. And you can have a monitoring of this landslide different times. See, the start of this landslide is for this date, and then the amount of landslide is increasing to one point, and then start to decrease. So this kind of information can easily be obtained using the interferometric SAR technology. This is the project that we were involved in the ITC in the Netherlands, and the main purpose was to calculate the amount of, let's say, deformation that is happening because of the geothermal plants, geothermal activities. And we see that there are some like injection wells. When they have injection wells, there was uplift. There was uplift in that area. When there was production well, there was subsidence. So with this technology, we could easily estimate the amount of uplift and subsidence. Again, the same project in the north of the part that we are working is the Bandung area in Indonesia. And it is really, there are a lot of water pumping in this case. You can see the amount of, these red areas shows the amount of subsidence just because of the water pumping. And also in Tehran also we have the same problem. There are a lot of water pumping. Yeah, and this was the last slide in my presentation. And if there is any question or comments. I really apologize because there were a lot of things that I have to cover, so in some parts I was very fast. I'm sorry for that.
Well, it was a tough tour. Say I never understood radar technologies as well as I do since today. Yes. So it was really an excellent talk. Thank you very much.
Thank you.
And small gift.
Yeah, thank you very much.
Excuse me. And yes, any questions?
I have a question.
Sure.
Yeah, in Bogota, there was a study and they measure subsidences. But then when they compare, when they try to validate the results were a little bit so pessimistic. And then we don't know why.
Yeah. Who did this?
University of Spain,
Okay.
Catalonia.
Yeah, I see.
And then they are trying to sell this again. And then they're saying, yeah, the substance are important. It's important that you measure this. But we say, but the results are not okay.
Yeah.
You validate them. What could be the reason for this?
Yeah. How did you validate, by GPS data or something?
Yes.
Okay.
Yes.
Yeah, because you know the interferometry studies were the basic. It is very complex. It is not as easy as these things that I show you. And for most of the cases, we need a time series of information. For example, 40 images, 50. If the number of images is not good, then the result could not be reliable. This could be one reason for that. For example, if you are using the Sentinel-1 data, the Sentinel-1 data up to now is not like a good coverage. You know, for example, we could not find like 40 images of one area with Sentinel-1 data. So one reason could be the number of images. And another thing, if I don't know what is the atmospheric condition in the region of your study, because if the atmosphere is changing too much, the modeling of the atmosphere is also a very difficult thing. So if you want to model the atmosphere with a very varying amount of atmospheric conditions, you need a lot of images if you want to model this one. If these conditions are met, I think the amount of estimation should be okay. Yeah. Yeah.
Thanks for the presentation. After the landsliding and earthquakes, can we actually radar some of hydrogen can be changed dramatically? How it impact on the output?
I didn't get your question.
Radar from hydrogen. So it's mean the subsurface hydrogen, the water temperature things. Can we have a change after the earthquake?
After the landslide, you mean?
Yeah. After the landsliding or earthquake, so subsurface hydrogen, the water content can be changed.
Oh, the water content after the landslide, you mean is changing?
Yes.
So the question is how to estimate this amount of changes?
Yes, but its impact on the out.
Yeah. Basically it can, yeah.
How do you model it?
Actually, we can just measure the amount of like displacement. The displacement could be to the water pumping, could be due to landslide, could be due to the fault, tectonics, whatever. So what exactly being estimated is just the amount of displacement. This is estimation. The modeling is another scenario. How to obtain the influencing parameter. Is it related to the water pumping or is it related to landslide? Is it related to fault? I mean, because the pattern of deformation in any of these cases is different. The deformation that we are expecting from an earthquake is totally different from the deformation that we see from the landslide, from water pumping.
Yeah.
So from these different patterns, we can usually find a model to see.
There's another question to ask how the
Moisture
in the soil
effect.
will affect, gives an effect if you have really wet bottom and take a picture and it's dry. So is there an impact on your result of the slide?
The water, the amount of water.
Yeah.
You mean water on the ground?
The moisture before and
It
after.
doesn't have any importance because here we are collecting the phase information. The water amount is impacting the amplitude, not the phase. So the phase is completely independent of the soil moisture difference before or after a scenario like earthquake.
But from the amplitude, could he derive the amount of moisture?
Using the change detection scenarios,
Like,
yeah. You can apply the change detection scenarios, but not using the interferometry. Using the amplitude information, not the phase. The phase is not impacted by the soil moisture difference in two different times.
Has there been any research regarding this?
Yeah, there are a lot of research for calculation of the changes that are happening. For example, the example that you said, before a time or after a time. But this is based on the amplitude, not the phase. Yeah.
So I have a question about in your formula for interferogram is equal to L flatness plus digital elevation model plus deformation plus atmospheric.
Yeah.
And you mentioned when you want to derive atmospheric displacement information, you need to subtract digital elevation model from that. So you can use any kind of digital elevation model, or the digital elevation model should derive from the interferometry?
No, you should use any type of digital elevation model. Actually, any type of digital elevation model can be used, but it should be converted to phase. There is a small equation for converting the topography into phase. And the accuracy of the dam is important, but it is not impacting the result that much. You know what I'm saying? For example, a 10-meter vertical accuracy dam would be sufficient for reducing or subtracting the dam effect from this scenario. It could be generated from any source. Yeah, but from interferometry, if you can obtain from interferometry, it's very easy. You know what I'm saying? Yeah.
Okay, last question.
Yes, last question. I'm still confused about you mentioning about ascending and descending
Okay.
part of radar and optical.
Yeah.
You said there is no ascending and descending, but that's a satellite feature, right?
That's a satellite feature.
Yeah, but optical also has
The
ascending.
same. It's completely similar. It can collect the descending, but because in the descending time it is night, the image is useless.
What is descending, or who is descending?
The
Satellite is
the
descending.
satellite when it is in
Okay,
descending
so your
condition,
point
it's
is the radar data has more useful during night. Okay.
Yeah.
Okay. But when we do this kind of change detection for radar, we should be take care of ascending data only or descending
that's
data.
a good question. Yeah, if we are using the interferometry start, we should just use ascending or descending. We
Either
cannot
one.
combine these two because they are in different models. You know? The phase information cannot be related to each other. They should be the same.
Well, thank you for your question, and let's give a cheers. Sorry, now how to continue?
Maybe we have a short break, 1 minute.